Hey guys, in this video we're going to be looking at stoichiometry and limiting reactants. So by the end of this you should be able to do stoichiometry problems. You should also be able to do limiting reagent or reactant problems, being able to calculate any amount of moles and grams of any of the reactants or products within the reaction itself, and you should be able to calculate percent yield of a reaction. In a balanced equation, this balanced equation itself is going to be relating the relative number of moles or molecules involved in a reaction. So this relative amount gives us information about anything within there. So our molar quantities are indicated by the stoichiometric coefficients of that balanced equation. So the molar quantities are indicated by the stoichiometric coefficients. In the balanced equation. And we can use that in order to find out how much of one substance we need versus another. So anytime we're in moles, we can directly relate the different things within there. And then once we have our number of moles, we can then determine our number of grams that are required to do a reaction. So let's kind of look a little bit at this. So stoichiometry is the idea that we have a relative quantities of reactants and products, and we use them in order to determine amounts of one product or reactant if we know amounts of another product or reactant. And we're always going to use a balanced equation here. So anytime we do stoichiometry problems, we always have to have a balanced equation. And within stoichiometry, we use that balanced equation to convert from one substance to another. So using our balanced equation, we can say, okay, in this particular case, for every 1 mole of methane, we need 2 moles of oxygen gas. And when those come together, we produce 2 moles of water and 1 mole of carbon dioxide. So we can use that balanced equation to tell us exactly how many of each of our substances we need if we have one of the other substances, or how much we're going to produce if we have one of the other substances. So using these molar ratios, so our molar ratios are given by the balanced equation. Using these, we can find out any substance, how much of a substance we need if we know how much of another substance we have. So a ratio is exactly that. It's going to be number of moles over one over the number of moles of the other. So if we wanted a molar ratio between methane and oxygen, for instance, we would have 1 mole of methane is equal to 2 moles of O2 based on our balanced equation. So our ratio would either be 1 mole methane over 2 moles oxygen, or 2 moles oxygen over 1 mole of methane. And we can use these molar ratios to convert from one substance to another. So if we already know our number of moles of oxygen that we have, we can use this first one to convert into moles of methane, and vice versa. If we already know our moles of methane, we can use this one to figure out how many moles of oxygen we need in order to fully react our methane. Okay? So when we do stoichiometry problems, the very first thing, we need a balanced equation. We can't do anything without a balanced equation because that tells us our relative amounts of everything. Then we're going to always, whatever unit we have, we're going to convert it into moles. The only way that we relate things within a balanced equation is with moles. So this balanced equation is saying that 1 mole of methane reacts with 2 moles of oxygen gas to produce 1 mole of carbon dioxide and 2 moles of water, or We could also do it as molecules, and that would be fine as well. One molecule of methane reacts with 2 molecules of oxygen gas to produce 1 molecule of carbon dioxide gas and 2 molecules of water vapor. So we have to have a balanced equation, and we have to put everything into moles. So if you don't know where to go to moles. That is the first step. After you go to moles, you can construct these molar ratios to calculate the amount of moles of a desired substance. So whatever substance you have, you need a molar ratio that takes you from that substance to another substance. So again, looking back at this equation, if we start out with methane and we want to go to carbon dioxide, we want a molar ratio that includes both of these species. Okay, we want the one that we are desiring at the end to be on the top of our molar ratio, the one that we want to get rid of on the bottom of our molar ratio. Okay, then you're going to convert your moles of your wanted substance, and then you can get your desired mass using your substance's molar mass. Okay, so using your molar mass, you could take whatever moles of wanted substance you got from number 3 and convert it into a mass, as most stoichiometry problems are actually looking for mass. You just have to go to moles because that's the only way you can relate them. You cannot relate grams and grams directly. So let's look at how we'd actually figure out our molar ratios. So take the following equation. We've got propane reacting with oxygen gas to produce carbon dioxide and water, so another combustion reaction. And in this combustion reaction, I've already balanced it out for you guys. So we want to figure out what our different mole ratios are. So I've got substances A, B, C, and D. I've just kind of labeled them A, B, C, and D for clarity. So when we're comparing A and B, we're comparing propane to oxygen, and we look, nothing's written in front of it. Remember, that is a 1. So we have a 1 to 5 mole ratio when we're comparing our propane to our oxygen. And when we do this, we can do our conversion factors one of 2 ways. We can either have our octane on the top, oxygen on the bottom, or the reverse. So if we want to put octane on the top, if we want to put propane on the top, it would be 1 mole of propane over 5 moles of O2. And then we could do the opposite of that, 5 moles of O2 over 1 mole of our propane. Comparing A and C, comparing our propane to our carbon dioxide. This is going to be a 1 to 3 ratio. And this is going to bring us to 1 mole of propane on top, 3 moles of carbon dioxide. Our other option, carbon dioxide on top, and our propane on the bottom. Next one, A to D, this one to this one, so our propane to our water. It's going to be a 1 to 4 mole ratio, and we do it the same way that we've done the other ones. So we have water on bottom or water on top. So you can literally convert between one substance to another, any one substance to any other substance within here. So we can go from B to C, 5 to 3, 5 moles of O2 for 3 moles of CO2, or 3 moles of CO2 over 5 moles of O2. We can go B to D, 5 to 4 mole ratio. And then lastly, we can convert between our products if we want to. So we could do C to D. So we have a 3 to 4 mole ratio. And that's pretty simple. And we can do that, again, anything we have within our reaction, we can convert to anything else in the reaction. Okay, so let's try an example. We've got 3.735 grams of iron metal, and we want to know how much chlorine gas we need in grams to convert all of our iron metal into iron 3 chloride, and then we want to know how much iron 3 chloride we produce. So we've got our steps over here. We see our first step is to balance our equation. So we'd put a 2 here, a 3 here, and then a 2 here. Then we're going to convert our units, our given units, which are 3.735 grams of iron metal, into moles of that substance. So we got 3.735 grams of iron. And on our periodic table, we see that iron has a molar mass of 55.845 grams. So we want that on the bottom, so we cancel out grams to give us 1 mole of iron. So we're going to take our 3.735, divide it by 55.845, and we get a value of 0.06682 moles of iron. Now we can use a molar ratio to go from moles of iron into moles of chlorine. So from our balanced equation, we see for every 2 moles of iron, for every 2 moles of iron, from our balanced equation, we see that for every 2 moles of iron, we need 3 moles of chlorine. So we're going to put 2 moles of iron on the bottom. So we cancel out our iron and our 3 moles of chlorine on the top. So we're going to divide by 2 times by 3, and this gives us 0.1003 moles of chlorine. And then we want to convert that from moles of chlorine into grams of chlorine. Remember, this is molecular chlorine, so we're going to have to take what's on the periodic table, 35.453, multiply that by 2 to get our molar mass, which is 70.906. It's a molar mass, so we're going from moles to grams. We want grams on top. That is our desired unit, so it would be 70.906 grams per 1 mole of chlorine. And we get 7.112 grams of chlorine gas that's required to fully react the 3.735 grams of iron metal. Last thing we want to do is we want to find out how much iron chloride we would produce. At this point, again, we can go from any mole substance to any other mole substance, so we can start back at moles of iron if we want, and that's where I'm going to start because there are 2 moles of iron per 2 moles of iron chloride, so it makes the most sense to me to just stick with that. But you could start with your moles of chlorine gas as well. So we have our moles of iron, and we know for every 2 moles of iron, we produce 2 moles of iron chloride, iron 3 chloride. So we're going to have 0.06682 moles of iron chloride, iron 3 chloride. And now we need to convert that into grams by using our molar mass of iron chloride. So we take our 35.453 for our chlorine, multiply that by 3, and then we add in the mass of our iron at 55.845. And this gives us an overall molar mass of 162.204 grams per 1 mole of iron 3 chloride. And when we multiply that out, we get 10.84 grams of iron chloride, iron 3 chloride. Now, I want to point out real quick that we are still observing the conservation of mass because we are talking about just a chemical reaction. So if we are not dealing with having anything in excess, our product amounts should be equal to our reactant amounts. And we see that when we look here. So we have 3.735 grams of iron. We have 7.112 112 grams of iron or chlorine, and then we have 10.84 grams of iron chloride. So if we take our 3.735 grams of iron, add it to our 7.112 grams of chlorine, what we should get is 10.84, or right thereabout. And what we get is 10.847 grams total, which represents our mass of iron chloride. This only works if we don't have anything in excess, but if we know how much reactant we have to fully react of both of our reactants or all three of our reactants, so we can figure out how much mass of product we should have. The masses of the products should equal the masses of the reactants. And that's what we found here. There's a little bit of rounding, right? So it's not exactly the same number because of rounding errors, but not a big deal. Okay, now, you may be wondering, how are we going to deal with volumes, right? It's pretty easy to go from mass to moles using our molar mass. But now we need to think about what we're going to do if we have a volume within stoichiometry. And when we're talking about volumes, there's going to be two different types of liquids. So two types of liquids. We are going to have pure substances and mixtures. Mixtures we are not yet able to deal with in the liquid form. We're going to look at it in the next unit. So wait on this. But these are going to be the ones that are shown in AQ. So AQ, that indicates that you have something dissolved in water. And that's usually the only type of mixtures we deal with when we're talking about stoichiometry. And then our pure substances, these are going to have the L in the chemical equation. And when we're dealing with them in stoichiometry, so dealing with pure substance volumes, we need to get this into a mass. And the best way to get a volume into a mass is to use your density. Remember, density is mass per volume. So if we have a volume, we use density, we can get into mass. So we're going to take our milliliters of our substance, multiply it by our density, which is in grams per milliliter generally, and that will give us grams. So it's our volume in milliliters. This is our density in grams per milliliter. And then this will give us our mass of substance. As I said, when we're dealing with mixtures in stoichiometry, we are going to wait on this until the next unit. In the next unit, we will actually talk about how to deal with those volumes. For now, we're just going to hand wave and be like, that's fine. Okay, let's try an example where we have ethanol, a pure substance, and look at how we would deal with that volume in this stoichiometry problem. So we've got 5 milliliters of pure ethanol. It has a density, that rho means density, of 0.789 grams per milliliter. It is combusted in the following combustion reactions. And we don't know how many grams of water is produced if it is exposed to air. So when we say exposed to air, that means we have an unlimited source of oxygen. So this is going to be in excess. Okay. Even here, we're going to start out the same way where we balance out our equation. And when we balance out our equation, we get a 3 here, a 2 here, and a 3 here. Okay. Next, we're going to want to go ahead and convert our units into moles. So we have 5.00 milliliters of ethanol, and we abbreviate that ETOH. And it's just a shorthand way of writing ethanol. So we're going to use our density, 0.789 grams per milliliter, to convert from milliliters of ethanol into grams of ethanol. And when we do this, we get a value of 3.945 grams of ethanol. And then we can use our molar mass of ethanol to go from grams of ethanol into moles of ethanol, where 1 mole of ethanol has a molar mass of 46.07 grams. So we'll take that 3.945, divide it by 46.07, and this gives us 0.0856 moles of ethanol. Once we have our moles of ethanol, we can go into moles of anything else within the balance equation. In this case, we want to go to water. So for every 1 mole of ethanol that is combusted, we produce 3 moles of water. So we're going to multiply this by 3, giving us 0.2569 moles of water. And then using our molar mass of water, we can go from moles of water into grams of water. So our molar mass of water is 18.015 grams per 1 mole of water. So we're going to take and multiply this by 18.015, and this gives us a value of 4.628 grams of water, and we have answered the problem. Okay, so what I have shown here is what's called our stoichiometry roadmap. So from here, we should be able to figure out where we need to go from any one substance to any other substance. So it doesn't matter what we label as A. It could be anything within the equation, and then anything we label as B is just a different thing in the equation. So if we have a pure substance, we need to use our density to get to grams. Once we have our grams, we can multiply by the reciprocal of molar mass of A to get into moles. And then using our mole to mole ratio, we can get to moles of B. Using our molecular weight of B, we can get to grams of B. And then if we want to go into volume of B, if it's a liquid, we can multiply by the reciprocal of density to get to a volume of B. Please note that there is no direct route from grams to grams. You have to go through moles. Okay, next topic I want to talk about is the idea of limiting reactants. So we're going to start with the talk about s'mores. So s'mores are a delicious treat where you take a marshmallow, some chocolate, and some graham crackers, you put them together, and you get a s'more, which is delicious. So if we were to take 1 marshmallow, half of a chocolate bar, and 1 graham cracker sheet, we would produce 1 full s'more treat, in my personal opinion. Some people like more chocolate, some people like less chocolate. But for my s'more, we have 1 marshmallow, a half a bar of chocolate, 1 graham cracker, thrown all together to make a delicious s'more. So if we take, to get whole number ratios, we multiply everything by 2. We get 2 marshmallows per 1 bar of chocolate per 2 sheets of crackers. These are our reactants. And our product gives us 2 delicious s'mores. Now, let's say we have 27 cracker sheets, 6 chocolate bars, and 64 marshmallows. Now the question is, how many can we make? So if we rely just on cracker sheets, we can make 27 s'mores. Just on chocolate bars, we can make 12 s'mores. And then just on marshmallows, we can make 64 s'mores. But once we've run out of something, we can no longer make any s'mores. So this is going to limit how many s'mores we can make. So this would be our limiting reactant. Once it's used up, we can't make any more. Okay, so these 2 are in excess. And we can determine how much excess we have by basically subtracting out how many we use to make these 12 s'mores, and then everything else would be considered excess. Now, this is a very simple example where we're using delicious, tasty s'mores, but we can apply the same thing to a chemical reaction. So when we talk about a chemical reaction, we're not always going to have the same or the right amounts of our reactants. We can have one thing in excess, and almost always there's going to be at least one thing that's in excess. And then there's going to be something that's going to be called the limiting reactant. The limiting reactant is going to be the reactant present in the smallest stoichiometric amount. So it's the one that gets used up first. Once it gets used up, the reaction stops. Like in the case of the s'mores. Once you use up the chocolate, it's no longer s'mores. It's just a marshmallow and a graham cracker. So it's something different. So once we've used up our limiting reactant, we can no longer have a reaction continue. So when we're doing limiting reactant problems, we always need to figure out first which one is the limiting reactant. And it's not going to be as simple as looking at chocolate bars. So first thing we're going to do when we start to do a limiting reactant problem, where we don't know which substance is the limiting reactant, we need to figure out which one is the limiting reactant. So a very simple idea of an actual chemical reaction with a limiting reactant. So we've got 2 molecules of H2 react with 1 molecule of O2 to produce 2 molecules of H2O. If we start out with 10 molecules of H2 and 7 molecules of O2, after the reaction proceeds, all 10 of the H2 molecules gets incorporated into 10 molecules of H2O. But only 5 of our O2 molecules are converted into H2O. So 10 H2 goes to 10 H2O. 5 O2 goes to 10 H2O. And we have an excess of 2 molecules of O2. So at the end of this, we're going to have 2 molecules of O2 left over. So we would say that our H2 is limiting and our O2 is in excess. And we can actually calculate how much excess we have. So let's look at our steps of our limiting reactant problems. First, balance. It's always going to be the first, is balance the chemical equation. After we've done that, we're going to convert everything into moles. When you're dealing with a limiting reactant problem, you're going to be given 2 reactants or 3 reactants, and you're going to convert all of them into moles. Then you're going to use stoichiometry to convert all of the individual reactants into one product. So we're going to convert all reactants into one product. If the chemical equation, or if you're producing only one substance, it's really easy. If you're producing multiple substances and it's asking for one substance, then it's easy. But if it's just trying to find out our limiting reagent, it doesn't matter which thing you go into. So just read the problem, look at what product makes the most sense to convert into. If one is not better than the other, it doesn't matter which product you go into. Just make sure all of them go into the same product. So only one product. Choose one product, convert all of them into that same product. Then the reactant that produces the least amount of product is the limiting reactant. Again, this is a limiting reactant, so it has to be a reactant. It will not be the product that's in limiting, it is the reactant that's in limiting. So once you've gotten your product, you're like, okay, which one of these reactants makes the least amount? Then you're going to go back. That reactant will be the limiting reactant, and all the rest of them will be in excess. So the rest of the reactants are in excess. Okay? And then you can find the excess reactant by subtracting the mass of the excess reactant consumed from the total mass of the excess reactant. So to find excess reactant amount, subtract amount of reactant consumed from starting reactant amount. Easy peasy. Let's try an example. Our first step is to balance our equation. And when we do this, we get the following equation. So we get 2 moles of octane for every 17 moles of O2, 16 molecules of carbon dioxide are produced, and 18 molecules or moles of water. So we're going to start out with 25.0 grams of octane. And when we calculate out the molar mass of octane, it is 114.23 grams per every 1 mole of octane. So we'll take our 25 divided by 114.23, giving us 0.219 moles of octane. And then we want to convert this into water because that's what it's asking for. So for every 2 moles of octane, we produce 18 moles of water. So divide by 2, multiply by 18, giving us 1.97 moles of water. We're going to do the same thing with our oxygen. So we have 30.0 grams of O2. For every 1 mole of O2, we have a mass of 31.998 grams. So we divide our 30 by 31.998, giving us 0.938 moles of O2. And then for every 17 moles of O2, we produce 18 moles of water. So we'll divide by 17, multiply by 18, giving us 0.993 moles of water. If we look, compare these two, we see that this one is the smaller amount. So oxygen is our limiting reactant. Okay. Now, once we have moles of water, we can convert it into grams using our molar mass. And we get a value of 17.9 grams of water produced. Pretty easy. Okay. We have something called theoretical yield and actual yield. Theoretical yield is the maximum amount of product that can be made during a chemical reaction. And this is theoretically, right? So how much we could theoretically make. This is based on stoichiometry and limiting reactants. So back here, our theoretical yield would be 17.9 grams. Based on stoichiometry, that is the maximum amount of water we can produce. Once we ran out of our O2, we cannot produce any more water, so this is the maximum amount of water we can produce. Right? It can be a little confusing. If you were to convert this into grams of water, this number would be greater, but that is not the theoretical yield because once we run out of our oxygen, we can no longer produce any more water, right? If we don't have oxygen, we can't make H2O. So this is our theoretical yield. From stoichiometry, it says this is the maximum amount we can make. Now, do you think a chemical reaction ever works that well? If you do, you are very optimistic. But what actually we get is our actual yield. The actual yield is how much is massed out by a researcher at the very end. So it could be after some purification, which you lose a lot of product during purification. So you're never going to have 100% yield. You're never going to reach that actual theoretical yield. So we always look at our actual yield as well, which is the amount actually produced and weighed, or produced and measured. Because you could potentially produce something that's a liquid and you could do a volume instead. Okay? As a general rule, actual yield and theoretical yield are reported in grams. Not in moles. Okay? That doesn't mean that it can't be given in moles, but it's usually not. Let's try and look. So let's look at something called percent yield and percent error. Our percent yield is how much the ratio of the percent of the amount that we actually obtained versus what could have been obtained. So percent of actual versus theoretical. So our percent yield will be equal to our actual yield divided by our theoretical yield times by 100%. And as a note, it does not matter if we're in grams or moles for this because the units will cancel out and our unit at the end is percent. Okay? You should have less than 100%. There should never be a percent yield that is at 100% or greater than 100%. And if you have less than 100%, which is going to happen, you've lost some product. Not a big deal. That always happens. You're always going to lose some product somewhere along the way, or something's not going to react completely. So you will always have a percent yield that is less than 100%. If you have more than 100%, magic has occurred. Or there's been contamination. So you probably haven't dried the substance well enough, or some of the reactant is still in there. So less than 100%, that is actually ideal, what you would expect. More than 100%, impossible. Actually 100%, not very likely. Okay, next is our percent error. So how much error that there is in the measurement. So an expression of the difference between the measured value and the actual value. And this is going to be equal to actual yield minus theoretical yield. We're going to put these absolute values over theoretical yield times by 100%. Again, doesn't matter what our yield is in, either grams or moles. It will give you a percentage at the end. And as a note, percent yield plus percent error will give you 100%. So together, they give you 100%. Okay, so let's try an example. Let's figure out what our theoretical yield is if we start out with 2.500 grams of aluminum metal and 5.00 grams of chlorine gas. So our theoretical yield, we only have one product, so that's what we're looking for our theoretical yield of. And if we produce 2.00 grams of aluminum chloride, what is our percent yield? So we're going to look at our theoretical yield and our percent yield. Okay, so as a note, first thing we need to do is balance our equation. So we're going to put a 3 here, a 2 here, and a 2 here, and we are balanced. This 2 grams of aluminum chloride, if you produce 2 grams of aluminum chloride, this is our actual yield. So what someone weighed out. Not in actuality, it's something I just made up, but we'll pretend. Okay, so we've got the startings. We're going to take each of our reactants, convert them into moles of aluminum chloride. So 2.500 grams of aluminum metal. So we're going to convert from 2.500 grams of aluminum into moles of aluminum. 1 mole of aluminum has a mass of 26.9815 grams. So we'll take our 2.500, divide it by 26.9815, and we get 0.09267 moles of aluminum. Then we're going to convert into moles of aluminum chloride. So for every 2 moles of aluminum, we produce 2 moles of aluminum chloride, giving us 0.09267 moles of aluminum chloride. Same thing with our chlorine. We have 5.000 grams of chlorine gas. It has a mass of 70.906 grams per 1 mole of molecular chlorine. So we take our 5 and divide it by our 70.906, and we get 0.07052 moles of chlorine. And then, using our molar ratios, 3 moles of chlorine gives us 2 moles of aluminum chloride, giving us a total of 0.04701 moles of aluminum chloride. That is the smaller amount. So chlorine is our limiting reactant. We now convert this into grams using our molar mass of aluminum chloride. So for every 1 mole of aluminum chloride, we have a mass of 133.3405 grams. Multiply that by 0.0407. Scratch that. Multiply that by 0.04701, and we get a value of 6.268 grams of aluminum chloride, and this is our theoretical yield. So now that we have our theoretical yield, we want to solve for our percent yield. Our percent yield is our actual yield over theoretical yield times by 100. Our actual yield is 2.000 grams of aluminum chloride. Our theoretical yield is 6.268 grams of aluminum chloride. Grams of aluminum chloride will cancel out, times by 100, and we get an abysmal 31.91%. Not a great percent yield. And then our percent error, we could just take this value and subtract it from 100, and we get a value of 68.09% error. That's a really large error. Not very good. Okay. That wraps up our discussion of our stoichiometry. I will talk to you guys later. Have a great day.